Hello and welcome. Phased array radars, advanced antenna system, and digital beamforming all shares one thing. They rely on multiple parallel transmit and receive channels. Synchronizing those channels isn't just important, it's critical. In large-scale systems, routing clocks and signals can quickly become a designer's nightmare. Is there a simple way to achieve deterministic synchronization without complex routing? Yes, sync chaining is a method to synchronize multiple ADCs using a single short pulse, 5 to 10 nanoseconds, that propagates through ADCs, aligning each to the master clock. It simplifies routing and ensures deterministic synchronization even after power cycles or environmental changes. The sync chaining method takes advantage of the deterministic sync propagation in the ADCs as well as the EasyStream's multi-lane alignment capabilities to enable precise and repeatable sample alignment. To demonstrate this, we set up a system using Teledyne's EV10AS940 synchronization kit with two ADCs. These ADCs are connected to an FPGA via HSSL serial links and EasyStream protocol. A common clock is distributed to both ADCs. The sync chain originates from the signal processing block, here the FPGA, not from a high-precision clock source, which makes it easier to route and less expensive. When the sync pulse exits the first ADC in the chain, it becomes synchronized with the master sample clock. This setup mimics a real-world phased array or MIMO system. A PLL generates a 12.8 GHz master clock while a generator supplies the input signal through a splitter. The input signals are matched in length and phase to ensure phase consistency. The sync signal is sent from the FPGA to the first ADC, which becomes synchronized. The synchronization pulse propagates from the first ADC to the second in a deterministic manner, aligned with the master clock. The resulting output waveforms show a phase delay due to propagation time between the ADCs. For the trailing phase, the input signal chosen is a low-frequency signal, which makes this delay easy to observe. For this system, the delay is 26 clock cycles, so we can compensate that by delaying internally the sync of the first ADC in the chain. We can use timer sync shift fine or cores, which are SPI register of the ADCs to correct this delay. Then, after a new sync pulse, we can see that the two ADCs are perfectly aligned. Additional delays could be tuned to compensate for the sync in and sync out variability to each ADC across temperature, but this has not been demonstrated here. After this training phase, once the different delay settings have been found, the synchronization will remain stable under all conditions. After a power cycle, an ACT event or a reset, you can simply reprogram the known settings and generate a sync pulse to obtain deterministic synchronization. Moreover, this alignment remains stable for all input frequencies. For example, with the exact same settings, the two ADCs maintain alignment even with a 23.1 GHz input signal. As a conclusion, we've seen how to synchronize two EV10AS940 ADCs using a shared clock, a chain sync signal, and a digital alignment. This method enables the development of precise, high-performance multi-ADC systems for radar, telecom, or imaging applications. If you have questions or if you are interested on the EV10AS940, please contact us using Teledyne E2V hotline email address. Thanks for watching.